Finding the inverse of a 2 by 2 matrix uses a simple formula. If our matrix M has entries A, B, C, D, then the inverse of M is D, negative B, negative C, A, and we'll divide by the determinant of M. Because we can't divide by 0, this shows why a determinant of 0 means the matrix is non-invertible. One way to keep track of this formula is we can say that we swap the main diagonal and we negate the weak diagonal. As an example, let's find the inverse of the matrix 2, 5, 1, 3. First, let's swap the main diagonal to get 3, 2, and we can negate the weak diagonal to get negative 5, negative 1. Lastly, we should divide by the determinant. Here, the determinant is 2 times 3 minus 5 times 1. We can check to make sure that we did our work correctly because we know that A times its inverse should be the identity matrix. Here, let's check. 2, 5, 1, 3 times 3, negative 5, negative 1, 2. Here we have 2 times 3 plus 5 times negative 1. So we'll have 6 minus 5. We'll have 2 times negative 5, which is negative 10, times 5 times 2, which is 10. We'll have 1 times 3, which is 3, plus 3 times negative 1, which is negative 3. And lastly, we'll have 1 times negative 5, plus 3 times 2. And sure enough, this does reduce to 1, 0, 0, 1. So this is in fact the inverse. In the context of system of equations, if we were given the system 2x plus 5y equals 3 and x plus 3y equals 1, then we could represent this as the system 2, 5, 1, 3 times xy equals 3, 1. Then we could say that using our matrix inverse, we can multiply both sides by our inverse matrix. Because we know that this is the identity matrix, we get that xy equals 3, negative 5, negative 1, 2 times 3, 1. This is a product that we can compute, and we would get 9 minus 5 and negative 3 plus 2, which would give us 4, negative 1. So our solution to this system is x equals 4, y equals negative 1. In this class, we'll use technology to find the inverses of matrices with dimensions greater than 2 by 2. However, we do still need to know how to work with inverses of these larger matrices. You will need to know how to check if a matrix is its inverse, and how to use the inverse to solve a system. This problem uses 3 by 3 matrices as an example of something that you will be expected to be able to do without using technology. Let's try to do the first part. We'll be using the fact that a matrix times its inverse is the identity matrix. So we want to ask, does 1, 0, 1, 0, 0, negative 1, 2, 1, 2 times 1, 1, 0, negative 2, 1, 0, negative 1, 0, 1 equal the identity matrix? Let's try to calculate it. The first entry would be 1 times 1, which is 1, plus 0 times 2, plus 1 times negative 1, negative 1, which is 0. This is immediately enough to know that this is not the inverse. If our first was A, and we call the second B, and this third C, we know that B does not equal the inverse of A. If we wanted to, we can check for our second matrix. And if we work through this slowly, we'll find that yes, it does in fact equal the identity matrix. So if A equals 1, 0, 1, 0, 0, negative 1, 2, 1, 2, then its inverse equals 1, 1, 0, negative 2, 0, 1, 0, negative 1, 0. To use this information to solve for this given system, we'll recognize that this system can be expressed as 1, 0, 1, 0, 0, negative 1, 2, 1, 2 times x, y, z equals 2, 4, 3. Because this is exactly what A was, we can find that x, y, z will equal A inverse times 2, 4, 3. So we get that x, y, z will equal A inverse times 2, 4, 3. Working this out, we will get that it's 2 plus 4, negative 4 plus 3, and negative 4. And then our final solution is that x equals 6, y equals negative 1, and z equals negative 4.